Hi everyone, welcome to my YouTube channel. Today we will be discussing about some important theorems in quantum mechanics. These are very important theorems to solve problems very easily. Let's begin. Theorem 1. For normalizable solution, separation constant E must be real. What is E? E is the constant we use to separate time part and space part of the Schrodinger equation, and we come up with the time independent Schrodinger equation. So let's prove that theorem. We know that the stationary states solution looks like psi equals to phi x e to the power minus iet by h. Now if E is a complex number, then we can write E equals to E1 plus IE2, where E1 and E2 are both real numbers. E is complex number. So we put E equals to E1 plus IE2 in psi and get this equation. And if we square psi xt, we get phi x square e to the power 2e2t h cut. So let's normalize psi xt. So the normalization condition is minus infinity to infinity psi xt square dx has to be 1, and we have already computed the value of psi xt square. Just put that in this equation and we get this, and e to the power 2e2t by h cut is independent of x, so we can take it out of the integral sign. And if this equation has to be true for all times, then E2 has to be 0, because if E2 is not 0, let's say for a very large time, let's say infinity, this equation can be true. But we know that for normalizable solution, the square integration of the wave function has to be 1, and that's possible only if E2 is 0. So from this we can say that E is a real number. Let's move on to the second theorem. We can always take the solution to time independent Schrodinger equation to be real. Actually the wave function can be complex, but we can always choose a real wave function with the same energy. Let's see how we can do that. 1D time independent Schrodinger equation is minus h cut square by 2m d2 psi by dx square plus v psi equals to e psi. We can take complex conjugate of equation 1 and we consider that V, or the potential, is a real quantity, and we have already proven that E, the separation constant, is also a real quantity. From equation 2 we can see that psi star, or the complex conjugate of psi, is also a solution to Schrodinger equation with the same energy E. Now let's say psi 1 and psi 2 are two solutions of Schrodinger equation with the same energy E, and let psi 3 is a psi 1 plus b psi 2, where a and b are constant, and now look for if psi 3 is also a solution of the Schrodinger equation, and that also with the same energy. It will be very fun. Let's do it. h cut square by 2m d2 psi 3 by dx square plus v psi 3 equals to, we have to put psi 3 as a psi 1 plus b psi 2, and then differentiate both of the term separately. Now let's collect the psi 1 terms together and psi 2 terms together, and we get the 1D Schrodinger equations in psi 1 and psi 2 separately. So they are equals to E psi 1 and E psi 2. So we have just written that. From here we can see that this is equals to E psi 3. So psi 3 is also a solution with the same energy E. From this we can say that if psi and psi star are real solution to Schrodinger equation with the same energy, then so is there any linear combination. If z is a complex number, we can write z equals to a plus ib, where a and b are real. So z star is a minus ib. Z plus z star is 2a, which is a real quantity, and I into z minus z star, which is minus 2b, which is also a real quantity. In the similar way, psi plus psi star and I into psi minus psi star are real quantities, and they both are linear combination of psi and psi star. So we can always construct two real solutions to the Schrodinger equation if psi is a complex function. From all these discussions, we can see that psi and psi star are the solution of the Schrodinger equation with the same energy E. So their combination psi plus psi star and I into psi minus psi star is also a solution to the Schrodinger equation with the same energy E. So it is always possible to choose a real function instead of choosing a complex function. That is what we are trying to prove here. In particular, we can write psi as half into psi plus psi star minus I into I psi minus psi star, where the psi plus psi star and I into psi minus psi star are both real. So from this we can say that we can write psi as a linear combination of two real solutions. Now let's move on to the theorem 3. If potential Vx is even function, then psi x can always be taken to be either odd or even. Let's prove that. We know the Schrodinger equation as minus h square square by 2m d2 psi by dx square plus v psi equals to e psi. Now if we change variable from x to minus x, and we know that d2 by d minus x square is d2 by dx square, so equation 2 becomes minus h square by 2m d2 psi of minus x dx square plus v minus x psi minus x e psi minus x. Now if v is an even function, we know that v of minus x equals to vx. So put that in equation 3. So equation 3 becomes minus h square by 2m d2 psi of minus x by dx square plus vx psi minus x equals to e psi minus x. Here we can see that psi minus x is also a solution to the Schrodinger equation with the same energy E. Any linear combination of psi and psi of minus x is also a solution to the Schrodinger equation with the same energy. Let's construct a odd and an even function. Let's say psi plus is psi x plus psi of minus x. Here we can see that psi plus of minus x equals to psi plus of x. So psi plus of x is a even function. Let psi minus equals to psi x minus psi of minus x. So we can write psi minus of minus x equals to minus psi minus of x. So psi minus x is an odd function, but psi plus and psi minus both are solution to Schrodinger equation because they are linear combination of psi x and psi minus x also with the same energy. So we can always choose either an odd or an even wave function if psi x is even, or we can write psi x as half psi plus psi minus, which is a linear combination of even and odd function. So let's move on to theorem 4. The energy E must exceed the minimum value of the potential Vx for every normalizable solution to Schrodinger equation. 1D time independent Schrodinger equation is minus h cut square by 2m d2 psi by dx square plus v psi equals to e psi, or d2 psi by dx square equals to 2m by h cut square v minus e into psi. So if E is less than V minimum, then psi and the second derivative of psi will always have the same sign. Let's take two cases. So case 1 is, if psi is positive, then the second derivative is also positive for all values of x. So the curve is always directed away from the axis. If we determine the first derivative of function and equate it to the 0, from there we can find out a point, and if we further do the second derivative and put the point on that equation and check whether the second derivative is positive or negative, from that we can determine whether the point is minimum or maximum. In this case, let's say this is the minimum point. How can we determine that? We have to equate the first derivative of psi to 0 and determine a point, and we can see here that the second derivative is always positive no matter what the value of x is. So we can find a minimum point of the function psi x, and for all other values of x, psi is greater than that. So we can infer that the value of the wave function at plus or minus infinity is infinity, but which is not a desirable condition, because we know that to represent a physically realizable solution, psi has to be 0 at plus minus infinity. So from here we can say that E must has to be greater than at least V minimum. And let's talk about the second case. If psi x is negative, then the second derivative of psi x is also negative. It always points away from the axis and is infinity at plus minus infinity. The same argument goes here. Let's say this is the maximum point. We can equate the first derivative to 0, and from here we can determine some value of x, and then we can see easily from here that for all values of x, psi double prime is negative. So we can say that this point is maximum point, and the value of the wave function at all other points, this whole area are less than this point. So it will never come back to the axis, to this axis. It will never come back. So it will reach infinity when x is plus minus infinity. That's why we cannot normalize this kind of functions. So E has to be at least greater than V minimum. So that's all for today. I hope you enjoyed the lecture. If you like my video, please subscribe and share. See you in the next lecture. Bye.